Okay, so let us start. So in the last lecture, we were discussing about these devices, right? So we talked about the diodes, the PN junction diodes, and then we also saw the the junction capacitance or linear capacitance, and then we also understood how to linearize this junction capacitance, and then we also talked about some secondary effects like Zener and avalanche effects in these diodes, and then we also understand the spice parameters associated with the diode model using spice simulations. And then we came on to our discussion on transistors, okay, that is MOSFET, and we understood the importance of this source to bulk bias or body bias that controls the threshold voltage. And we also understood the components of the threshold voltage, that is on what factors the threshold voltage depends. Okay. Now let us come on to this mode of operation here in MOSFETs, that is linear mode of operation, right? So when you apply a VGS, okay, so for creating a channel, first of all, you need to apply a VGS which should be greater than the threshold voltage of the MOSFET. Okay. So once you fulfill this condition, a channel is created. Okay. A channel like this is created. Okay. Now, once a channel is created, you can think about applying a VDS, that is a positive voltage at the drain side, right? At this terminal, you can apply a bias. So VDS you apply here, and so you already have a channel here. So conduction is possible, that is electrons will flow from source to the drain via this channel. And because of this electron flow from source to drain, you will see current flowing from drain to source, right? So current you will see from drain to source, that is IDS, you will see when you apply a VDS. Okay. Now the channel here, okay, so this channel, so the potential of this channel, so this is not fixed, not constant. So this keeps changing as you move from source side, that is from this point to the drain side. So the channel potential, that is, let us say channel potential is Vx. So this Vx varies as you move from source to drain. So for example, the value of Vx at this point, okay. So at this point, the value of Vx, so that would be equal to 0. And the value at this point, so the value of Vx at this point, that is channel potential at this point, so that would be equal to Vd, that is applied bias at the drain. So whatever you apply at the drain, so the channel potential would be equal to Vx should be equal to Vd at this point, that is at L, right? That is x is equal to L. Let's say this is x is equal to 0 and this is x is equal to L, right? So the channel potential, that is Vx, this varies from as you move from source to drain. It is minimum or 0 at this point towards the source, and it keeps on increasing, okay, and it is equal to Vd, that is applied drain voltage at this point, at the end of the channel, right? That is at this point. Okay. Now to maintain a channel over here under the gate, so there is a condition that your Vg minus Vx, so that should be greater than Vt, threshold voltage. So this is the condition for maintaining a channel under the gate. Okay. Now since this Vx is varying, that is it is increasing as you move from source to drain. Okay. So that means this condition Vg minus Vx, so this also changes as you move from source to drain. Okay. So for example, when Vx is 0 at this point, so Vg is then greater than Vt. Okay. Now, as you move from source to drain, Vx increases. Okay, so when Vx increases, so this overall Vg minus Vx, so this reduces. Okay, so as you move from source to drain, this Vx increases, and because of this increase in Vx, the overall Vg minus Vx, this reduces. Okay? And in fact, at this point, that is where Vx is equal to Vd, and if let us say Vd is equal to Vg, let's say, or maybe let's say Vd is greater than Vg. So this Vg minus Vx can even be, negative, right? Even smaller than Vt. So, this channel, that is presence of channel, depends upon the applied drain to source voltage. So if the drain to source voltage is of high, that is normally at this point it is very high. So when you keep on increasing this VDS, so there will be a level of VDS where you will find that Vg minus Vx, that is channel potential, that will be less than Vt. So at that point, ideally there should be no channel, okay, which is also called a saturation condition, that is channel saturates. Maybe let me take a screen over here. Let us try to understand this. Let's say this is my N-channel MOSFET. So I have N plus source and drain diffusion regions. Okay. And my P-type substrate over here. And let's say I have a gate with SiO2. Now, when you apply a bias over here, in fact, when you apply a bias over here, Vg, say positive. So Vg is applied between Vg and bulk, and bulk and source are connected. Let's say source is grounded. So I'll simply say source is grounded. So bulk is also grounded. Let's say. Okay, I'll take one more screen. So let's redraw. Yeah, so I apply a positive Vg and source is grounded, let's say, and bulk is also grounded. This bulk is also grounded. Now when you apply a gate bias, so that means you are applying an electric field, that is a vertical electric field is applied. Okay. And you have a depletion region here then under the gate. Okay. Let's say you have a depletion region under the gate, okay, because of this applied bias Vg, which is now positive. So because of this, you have a depletion region under the gate, and then if you increase Vg further, and if Vg is greater than Vt, so you will see a channel also here, that is inverted channel, that is you have electrons under the gate, and through this channel, if you apply a drain bias over here, Vd positive, some positive Vd, so through this channel, now the current can flow from drain to source. Okay. Yeah. So when you are applying a VDS, so that means you are also applying an electric field, which is originating from drain and terminating at source terminal. So you have another electric field, which is horizontal electric field. Now since Vx, that is the channel potential, this is varying, and this is 0 at this point. So Vx is 0. And Vx at this point, so this is equal to your Vd. Okay. So obviously, when Vd is increased, let's say Vd, so this keeps on increasing. So the channel potential, so that also increases from source to drain, right? So maybe let's say the channel potential increases and it reaches VD at a channel length of L. Okay, and let's say this is x is equal to 0 point where my Vx is 0, and this is x is equal to n point, L point where my Vx is equal to Vd. So the potential profile of the channel is, that is, this is increasing. So Vg minus Vx, that is this Vg minus Vx, which is a sufficient condition required, that is Vg minus Vx, that should be greater than Vt. So this also changes as you move away from the channel. Okay, that is Vg minus Vx. So this is maximum. Yeah, so Vg minus Vx is maximum at this point, which is, let's say, x is equal to 0 point, and it reduces when you move to x is equal to L point, right? So this is Vg minus Vx. So this changes as you move from source to drain. So obviously Vg minus Vx, that is, this is my sufficient condition to create a channel, and Vg minus Vx is varying this way. Okay, so that means my channel, that is this channel, this should also not be constant, because my Vg minus Vx, that is channel potential, that is total channel potential, okay, that is Vg minus Vx, this also varies this way. So the channel should also not remain constant. So the channel should take a shape of, somewhat of this kind. Maybe let me use another ink. So the channel shape should actually be of this kind. Okay, because my Vg minus Vx is dropping as I move from this point, that is x is equal to 0 to x is equal to L. This is my channel length, so this is x is equal to L point. So when I move from x is equal to 0 to x is equal to L, my Vg minus Vx, so this drops. So when Vg minus Vx drops, so obviously the channel cannot be held constant. Okay, the channel, this will also change. So in fact, the channel will be somewhat of wedge shape. Okay? And at this point, if Vg minus Vx is less than Vt, okay, so again Vx depends, Vx is equal to Vd here at this point, and let's say Vg minus Vx is less than Vd. So I'll reach a pinch off point over here, that is at the verge of saturation. And now if Vd is further increased, right, then Vg minus Vx will be less than Vt. Okay, maybe at this point also you will see, maybe if Vd is further increased, you will see at this point also Vg minus Vx is less than Vt. So the channel will be further reduced. It will come here at this point. That means between these 2 points, I don't have a channel now. So the channel is only present between these 2 points, because Vg minus Vx in this region is not greater than Vt or equal to Vt, because my Vd is increased. Okay, so I don't have a channel here. Okay. Now because I have increased this Vd, so that means I am increasing the reverse bias across the drain bulk junction. Okay. Source bulk junction, the reverse bias is fixed, but when you increase Vd, that means the reverse bias across the drain bulk junction also increases. So when reverse bias across the drain bulk junction increases, so what will happen to the depletion region? So the depletion region will widen under the drain. Okay. And also because of the same effect Vd, that is you are increasing Vd, now the channel is tapered now, that is of wedge shape, that is some electrons are now missing here in the channel. Earlier it was straight, but now it is of wedge shape. Okay, so that means some channel charge are lost here. So to accommodate that lost channel charges, your depletion region under the gate, so that should also vary in a similar fashion. Yeah? To fulfill that space charge neutrality principle. That is, when channel charge is lost, so equivalent depletion charge will be added. So that means my depletion region, so that will not remain like this. So let us try to draw the depletion region in this case. Let us take another screen. So let us try to draw the depletion region in this case when the MOSFET, VDS, that is the drain bias voltage, is increased, and when it is at the verge of saturation. So this is my N plus again. This is P type. So I have increased my VD. Let's say VD is greater than, let's say, VGS minus VT. That is the saturation condition. So my VDS is greater than VGS minus VT. So how is the channel now? So since I'm increasing my VDS, as I said, so since I'm increasing my VDS or I'm increasing my VDB, that is, I'm increasing the reverse bias across the drain and bulk junction. Okay? So that is increased now, but reverse bias across the source and bulk junction, so that is still the same. So the depletion region around the source, so that will remain more or less same. Okay, and now my channel is also tapered like this. It is not constant, it is tapered. So to accommodate this change, that is, channel is becoming tapered, that is, it is taking a shape of this kind. So my depletion region will also change, right? So depletion region will, maybe it will look like this now. Okay, and that is because of the space charge neutrality principle. That is, space charge in this region should be constant. So if you are removing some charge from the electrons you are removing from the channel because of this applied bias VD, so obviously the space charge here, so that should increase. Now VD is now, that is drain to bulk junction, so that is for the reverse bias is further increased. So under the drain you will see that the diffusion, that is the depletion region, so that further widens. Now the depletion region may look somewhat like this. Okay, now when further VD is increased, VDS is further increased, okay, very, very large, then VGS minus VT. So that means this depletion region under the gate, this will further increase. So to accommodate this change, that is increase in the depletion region under the drain, the channel charges towards the drain side, so that should be removed. Okay. So that means my channel will change further, and now it may look like this. Right, it may end up here. So I have, that means no channel in this region. So this region I have no channel delta L, but still the current flows from drain to source. There is no channel in this region, that is delta L, but still the current flows. Okay, and why the current flows? Because in this region you have very high electric field. So this electric field, high electric field, because of this high electric field, the electrons fly away from the channel to the drain. But yes, the current becomes constant. Okay, that is saturation condition. The current of the MOSFET becomes constant, almost constant, saturates. And in this region, the MOSFET can be used as a constant current source. In fact, you will find that because of this channel length modulation, okay, that is, the channel is reducing now. So earlier it was, the channel was from here to here, that is L, complete L, but now the channel is only up to this point. That is, my channel is reduced now, or channel length has modulated or reduced. So now the channel length is L dash. So because of this channel length modulation, that is reduced channel length, you will see that current increases. Okay. So let us try to look at how the current is modeled. So in a long channel device, the current is modeled by this relation. Okay. That is ID, that is current, is in linear region, the current is given by ID is equal to, this is mu n Cox, that is process transconductance parameter, multiplied by W by L, VGS minus VT into VDS minus VDS square by 2. So this is for linear region. So in linear region, the current is modeled or calculated by using this relation, where Kn prime is process transconductance parameter. Okay. Now in saturation mode, that is when VDS is greater than or equal to VGS minus VT. Okay. So for this, you will simply put VDS here as VGS minus VT. So put VDS is equal to VGS minus VT in this equation. VDS is equal to VGS minus VT in this equation. Okay. So when you put VDS as VGS minus VT over here, so this becomes VGS minus VT whole square minus VDS minus VT whole square by 2. Okay, so this becomes VGS minus VT whole square divided by 2. That is here. So ID is given by now Kn prime W by L, VGS minus VT whole square by 2. Okay. Now to incorporate the effect of channel length on the current, okay, a factor counting for channel length modulation, that is lambda. So this is included. Okay. So to model the effect of channel length modulation on the current, we include this factor lambda. Okay. So which will which is called a channel length modulation parameter. So you multiply the drain current by 1 plus lambda VDS to model the effect of channel length. So the effect of channel length can also be seen from here. So what happens if my L goes down? So let's say my channel length goes down here. Yeah? So which was actually happening over here. The channel length is actually now this much only. That is L dash, let's say. So earlier it was this much, but because of channel length modulation, channel length is modulated and it has become small. So what happens when my channel length becomes small here? So the current should ideally increase, okay, because channel length has reduced. So that's why you will see when you simulate or when you calculate the behavior using this equation, okay, you will see that the drain current actually increases during saturation here like this. So it saturates, and when the channel length further modulates, it increases, right? So this is drain current, it increases. Okay, at this point, the channel length modulation comes into picture, that is channel length becomes significantly small. And this is ID versus VDS. And these are all VGS, that is, you're increasing VGS. Okay, maybe VGS is equal to, let's say, 1 volt here, and here maybe VGS is equal to 1.5 and so on. So the effect of channel length modulation is that the current increases in saturation. Okay. So the current should, saturation means that current should be constant, so that the MOSFET can be used as a constant current source. But if you further increase VDS, that is, the channel length is further shortened or modulated, the current will be increased. Yeah, that is evident from this modeling equation.
Sir, excuse me, sir.
Yeah, please.
Sir, channel and modulation parameter is used only if MOSFET is in saturation region.
Correct.
Then, sir.
Correct. Yeah, correct. So channel length modulation only
But
comes into picture when MOSFET is in saturation region. So that is why the saturation region equation is, this is my, saturation region channel equation. So where I have included lambda, but here in linear region, there is no need for this lambda. So
sir,
linear,
means in linear region the channel length does not change, sir. It will be constant.
yeah, definitely it will always be constant, linear region, where your VDS is less than VGS minus VT. So the channel length does not changes. But in,
Hello, sir.
yeah, please.
Okay, sir.
Sir, I have a doubt. Sir, in this MOSFET, we have connected the source to the ground and the drain terminal to some voltages. Sir, what if we reverse? Like what if we connect the ground to the drain, and we increase the source voltage and keeping the gate voltage high enough so that channel has been in this region. So what if
Correct.
we increase the source voltage and so does the
Yeah,
channel
channel will
will
form
get
like
pinched
this.
off?
Yeah, pinch
Okay,
off will be there, and the current will be now from source to drain in this situation. So when you are
sir.
making this positive and this negative,
Okay,
so current will be from source to drain, and electron will move from drain to
sir,
source.
Sir, from source to drain, or sir, we call now source.
Yeah, now you call
Source
source as
replace.
drain.
Yes, sir.
Correct. So source means obviously a source
okay,
of
sir.
carriers, right? So in MOSFET, you can interchange these two terminals. So since you're applying a bias, positive bias at this terminal, so you will call this as drain. So the electrons or the carriers will be collected here. So other terminal you can call source. So these things can be interchanged, source or drain, depending on what kind of bias you are applying. So source means obviously a source of carriers. Yeah, anything else? Okay. So channel length modulation, that is lambda, we do not include in linear region. So linear region, the diode current, sorry, the transistor current is modeled by this relation where you don't see lambda. So lambda, you put as lambda as 0 in the linear region. Okay. But in saturation mode, you need to include this channel length modulation parameter, because you see that because of this reduction in channel length, the current can increase. So to model this effect of channel length modulation, you include this lambda as a parameter. Now, for a model for manual analysis could be that you replace, or you put between drain and source voltage control current source ID, and that voltage current control current source ID is given by the same equation for the current MOSFET current in linear region. Sorry, this is for saturation region, that is VDS is greater than VGS minus VT. And the next one is, that is this one, this is for linear region. And VT is again given by the same previous equation that we had studied, that is zero bias threshold voltage, which is process dependent, and body effect coefficient, and source to bulk bias, that is body bias, and also the Fermi potential, which is given by the difference in intrinsic level and the Fermi levels. So this is model can be utilized for manual analysis of the MOSFET circuits based on MOSFETs. Now, previously we had seen the IV characteristics of a long channel MOSFET. So let me go back here. This one. So we had seen previously, yesterday I think, the current voltage relationship of a long channel MOSFET. So we saw that the current levels are some, let's say the drive current at 2.5 voltage, somewhere around 5 into 10 to the power minus 4, maybe 50 milliamperes. Okay. And the current voltage relationship had a quadratic relationship, okay, which was observed by looking at the spacing between the current at different VGS. Okay. Now, if we talk about long channel devices, sorry, short channel devices, So we come on to the short channel device. So short channel device may be somewhere around 0.25 micron channel length. Okay. The IV characteristic is almost similar, but here you will find that because of this effect, that is short channel effect, one of the short channel effect is velocity saturation, right? Because in a short channel MOSFET, the channel length is short, so the electric field in the drain to source region is also very high. Okay? Now the electrons in the channel, or the carriers in the channel, they because of scattering due to collisions, they this velocity saturation effect, they feel the effect of velocity saturation, that is carrier velocity saturates because of scattering due to collisions, okay, in the channel, right? So because of this velocity saturation, you will see that short channel MOSFET experiences early saturation, okay? That is at lower values of VDS, the MOSFET saturates. And because of this early saturation, the current levels are also not very high. That is the current drive, that is also affected. So here you will see that maximum current you can obtain is somewhere around 2 into 10 to the power minus 4 ampere it's showing. Okay. So yeah, 2 into 10 to the power minus 4 maybe. But in the long channel MOSFET for same VGS and same VDS, okay, let's go back. So in a long channel MOSFET, for VGS is 2.5 and let's say VDS is 2 volts, you are seeing a current of somewhere around 5 into 10 to the power minus 4 ampere. Okay. But in short channel, you are observing at 2 VDS, 2 volts VDS, and VGS is 2.5 volts, you are observing only somewhere around 2 into 10 to the power minus 4 amperes. Okay. So that means the current drive of the MOSFET is also reduced. That is current swing, that is current, high current levels are possible in long channel transistor, but because of this velocity saturation, my short channel MOSFET, this saturates early. That is at lower values of VDS, the MOSFET saturates. So the current drive is not much. So for low impedance current source, one can utilize the long channel transistor, right? So short channel transistor should not be used for low impedance current source. For this application, long channel transistor can be utilized. Now this IV characteristics, so this has a linear relationship with VGS, that is I varies linearly with VGS. So this is important here. So it varies linearly with VGS, but there in the long channel, the IV characteristic showed a quadratic relationship, that is I was varying quadratically with the applied VGS. Right, so channel length modulation we had seen already, that is because of the reduction in channel length, the current was increasing. So that can be modeled by bringing in this parameter lambda, which is a channel length modulation parameter. Yeah, and then this velocity saturation, this happens at a critical electric field, that is between drain and source. If a critical electric field of somewhere around 1.5 volts per micrometer is achieved. Okay, so when this reaches, and this generally happens only in short channel devices, that is this velocity saturation effect. So at somewhere around 1.5 volts per micrometer, the carriers in the channel region, they collide with the atoms in the silicon lattice, and because of this collision, scattering may result, and this saturation, that is velocity of the carriers, may also saturate or reduce. Okay. And saturation velocity is somewhere around 10 to the power 5 meter per second. Okay. That is, the carrier velocity was earlier, it was increasing, okay, but because of this velocity saturation, the velocity saturates, that is, it becomes constant now. Okay. So when it becomes constant, the current also is affected. Okay. If it keeps on increasing, then one can expect current will also increase, but when it saturates, so current also saturates after some time. Now this critical field, that is critical electric field, at which the velocity saturation happens, it depends upon the doping levels and the applied electric field. Okay? So two things are important, that is doping levels and the applied electric field. Okay? So velocity saturation depends on two factors, that is doping levels and the electric field. Okay? Now for electrons, this critical electric field, this varies between 1 and 5 volt per micrometer. Okay? And for holes, so we need some higher field, somewhat higher field is required for holes in a N-type silicon to achieve saturation. Okay? Therefore, velocity saturation effects are less pronounced in PMOS transistors in comparison to the NMOS transistors. So here is a comparison of the currents in long channel device and a short channel device. So you will see here that because of this velocity saturation, the VDS, that is saturation voltage, okay, so that is small now, yeah, that is reduced, that is early saturation we are seeing at small values of VDS, right? So but here in long channel, VDS is, unless VDS is equal to VGS minus VT, the MOSFET doesn't saturate. But here, even if my VDS is less than VGS minus VT, the MOSFET saturates. And because of this saturation, the current drive of the MOSFET suffers, that is current that can be achieved from the maximum current that can be achieved is smaller than what can be achieved by a long channel MOSFET. Yeah? So this is my saturation current, for example, in the long channel MOSFET, and this one is for short channel MOSFET. So huge differences can be observed. Now, apart from this velocity saturation, which is a second order effect or short channel effect, so there are more effects, for example, DIBL, a hot carrier effect, punch through effect, and also mobility degradation. So one of the effects is called mobility degradation, that is the carrier mobility also suffers or it reduces with increase in VGS. Okay, so this time the mobility degradation is because of the applied VGS. So VGS creates an electric field which is pointing from top to the bottom, right? That is VGS, you apply VGS, that is positive, gate is positive and bulk is negative or source is negative. So you apply electric field from the gate. So the origin is from the gate and termination is towards the bulb. And you also have another electric field because of VDS, okay, which is causing my electrons to flow from source to drain. Okay. Now because of this vertical electric field, the electrons may feel a force that can drive these electrons towards the gate surface. Okay. Instead of moving this way, that is from left to right, that is from source to drain, because of this field, that is the vertical electric field from the gate, the electron experiences, instead of going this way, they may, try going, this way, right? That is source to drain, instead of going straight, maybe because of this electric field, that is vertical electric field, they may experience somewhat deflection. Okay? So that deflection actually causes this effect, which is called mobility degradation. Okay? That is, it reduces the surface mobility with respect to the bulk mobility. Okay? So this is modeled by this effect of this mobility degradation, that is how much mobility is degraded or reduced. So that is modeled by this equation, where this mu n0 is the bulk mobility, okay? Mobility of the bulk atoms in the silicon, divided by this 1 plus then VGS minus VT. This is a constant or empirical parameter, and then VGS minus VT. That is, this effective mobility depends upon the applied bias across the gate. So you increase VGS, okay? You increase VGS, the strength of this electric field becomes large, okay? And the effective mobility is further reduced. Yeah? So you increase VGS, let's say, you increase VGS, this effective mobility, this reduces. Okay? So this is also a very important parameter, and because of this also you will see that drain current reduces. So apart from velocity saturation, we have this effect also playing into picture. Now here is a comparison of those two devices, that is the long channel device and the short channel device. Okay. So in the short channel device we noticed drop in current drive, okay, because of the short channel effect, that is velocity saturation effect was there in the short channel device. So because of that there was a drop in current drive. So maximum current is you can see, so this is very small compared to what you achieve in a long channel device. Okay. And yeah, this is IV characteristic of short and long channel device. Now, to have a conduction of current, that is current to conduct from drain to source, you need to apply a VGS that should be greater than VT. So that doesn't mean that below VGS less than VT there is no conduction. Yeah. So in fact, it would be not okay to assume that the current suddenly changes when you apply VGS greater than or equal to VT. So that is not true actually. Okay. So there is always some current flowing at lower VGS values also. That is, at VGS less than VT also, you will find some current flowing through the MOSFET. Okay. So this is because of a weak inversion channel. Maybe the channel is there, but it's very weak. Okay. So because of weak channel or weak inversion channel, the conduction is still possible, that is current is still possible even when VGS is less than VT. So that defines my sub-threshold region of operation, or when there is a weak inversion. So because of this sub-threshold region of operation, or when the channel is not completely formed, still there can be conduction between drain and source. Okay. But yes, of course, the current levels will be small. So you will not obtain high current levels unless the channel is completely inverted or created. Okay, so the current levels may be small. Now in the sub-threshold region, the current actually increases exponentially. In this picture, you may not see any exponential rise in the current, okay, because you see that below VT, that is below 0.4 volts maybe, you will see that current is almost zero. Okay, so that exponential growth, that is the sub-threshold region of operation, that is not visible in this plot. Okay, but if you plot the same IV characteristic in logarithmic scale, which is being done over here, so ID is plotted in logarithmic scale. So you will notice here in this region, the current increases exponentially. Okay, this is an exponentially rise in the current in this region, that is below the threshold voltage. Okay. However, the current levels are of course very small. Okay, so for example, from 10 to the power minus 11 to 10 to the power minus 8, okay, or maybe 10 to the power minus 9. Okay. Only that much current is there. Okay, the current levels are small, but yes, there is still conduction. Okay, this is undesirable. We don't want that. We want to, in digital circuits, digital integrated circuits, we want the MOSFET to be completely off so that it can act as a perfect switch. That is, when you don't want to conduct, so switch is off. You want to conduct, switch is on. Right. So this is an undesirable thing, but yes, because of this sub-threshold region of operation, the MOSFET still conducts at VGS less than VT. Okay, and during that VGS less than VT portion, you have an exponential, rise in current. Okay. Then one of the performance metrics of a MOSFET could be sub-threshold slope. Yeah, so this sub-threshold slope is one of the performance metrics of the MOSFET. That is, if your sub-threshold slope is good, you will say my MOSFET is good. So what is this sub-threshold slope? So this actually defines that sub-threshold slope means that how much VGS should be reduced so that the drain current can be dropped by a factor of 10. Okay. So that is given by this sub-threshold slope. Okay, that is how much you reduce your VGS. Sub-threshold slope means that is, let's say, delta ID by delta VGS. That is how much VGS I should reduce so as to reduce current by a factor of 10. So why this is important? So in digital circuits, it is easy to switch on the devices, but sometimes it becomes difficult to switch off the devices. Okay? So to switch off the device, you will obviously reduce this VGS. Okay? So if you reduce VGS, ID should also reduce. Okay? So how much VGS should be reduced so that my current drops by a factor of 10? Okay? So this explains my sub-threshold slope. Okay? Now this sub-threshold slope is given by this relation, where n is normally 1 to 1.5. Okay? Now if you keep n as 1, okay? So you keep n as 1, this sub-threshold slope comes out to be somewhere around 60 millivolts per decade at room temperature, which is actually the best possible sub-threshold slope. Okay? Then if you keep n is equal to 1.5, the same sub-threshold comes out to be equal to 90 millivolt per decade. So what is this 60 millivolt per decade and 90 millivolt per decade, and which is the best one? Whether 60 is good or 90 millivolts per decade. So 60 millivolt per decade, for example, here means that you reduce your VGS, that is, you reduce your VGS by 60 millivolts, so that the current reduces by a factor of 10. Okay? So you have to reduce your VGS by a small amount, that is 60 millivolt, and the current reduces by a factor of 10. Similarly, 90 millivolts per decade means you reduce your VGS by 90 millivolts to see the same effect on the drain current, that is drain current reduces by a factor of 10. Okay? So obviously this means that the 60 millivolt decade per decade sub-threshold slope device, that can be switched off faster. Okay? So you can turn off this device which has 60 millivolt per decade sub-threshold slope. So this device can be turned off faster than this device which has a 90 millivolt per decade of sub-threshold slope. Okay?
Sir,
So this is one of the performance metrics, and
hello,
this
sir?
tells us that how much. Yeah, please.
Sir, we can choose any value of n, or it depends on something, sir.
Again, this depends upon process parameter. This is also again a process parameter. So normally it is between 1 to 1.5. 1 is the best case, okay, not possible generally. And normally, this can be achieved, that is 90 millivolt per decade can be achieved, but it is very hard to achieve this 60 millivolt per decade. So n is between 1 to 1.5. This is again given by the foundry.
Okay, sir.
Okay. So yeah. So that is sub-threshold slope tells me how much VGS should be reduced to reduce current, that is drain current, by a factor of 10. That is how quickly my device can be turned off. So if my sub-threshold slope is good, that is 60 millivolt per decade is the best one. So I say that I need only 60 millivolt change in VGS to create a change of a factor of 10, that is drain current reduces by a factor of 10 if I reduce my VGS by 60 millivolt. So this is better than this 90 millivolt. Okay, but yes, this is very hard to achieve 60 millivolt per decade. So my N-channel MOSFET, as we discussed, the IV characteristics, they look like this. Okay, so they are in the first quadrant. Now for a PMOS, the IV characteristics are in the third quadrant. That is, everything, all variables are assumed negative here. Okay? That is, your ID is also negative, and your VDS is also negative, and your VGS is also negative. So the IV characteristics lies in the third quadrant, right? So PMOS transistor. Now in SPICE, you will find a transistor model. Okay. In fact, that same transistor model can be also utilized for manual analysis. So on paper, you can calculate the circuit parameters. Okay, if you use this manual model, this is also in the SPICE model file also. So this tells me that for NMOS, VT naught, that is zero bias threshold, voltage, so that is somewhere around 0.43 volts. Gamma, that is body effect coefficient, that is somewhere around 0.4. VDSAT is 0.63. Then process transconductance parameter is this much. Lambda is this much. Okay. Similarly for PMOS, VT naught, all values are negative. Yeah, so this is the difference you will notice first thing. That is all values are negative. That is VT naught is negative, minus 0.4. Then gamma is also negative, minus 0.4. Okay. So all these values can be utilized to calculate the circuit parameters for any circuit on paper. That is for manual analysis, one can utilize these parameters. In fact, for SPICE simulations also, one can utilize these parameters for a 0.25 micron CMOS process. So for each process, these parameters will be different. So these parameters will not remain same for each process. So these parameters are only for 0.25 micron CMOS process. So for other CMOS process, these parameters will be different. Now, in a MOSFET, we said that the MOSFETs are used as switches.
Mufid is asking some questions, sir, I think.
Yeah, please, Mufid.
Sir, in chat box, he write.
Maybe. Yeah, gamma. So gamma is body effect coefficient. Okay. So a MOSFET is used as a switch. Now, obviously, this switch has some resistance because unless you have a channel, the resistance is very high. Okay? So when you have channel, again you have some on resistance because of that channel. The channel also has some resistance, so there is some on resistance. Okay, and this on resistance, that is channel resistance, this varies with the applied gate bias. Okay, so that means it's a non-linear quantity. So one has to linearize, that is fix its value or constant, make the value constant of this resistance for manual analysis or for even circuit analysis. So if my region of operation is, normally we have two regions, high or low. So on resistance can be linearized to have some fixed value, that is equivalent resistance. It can be replaced with some equivalent resistance. Okay. So let us say how it is done. So this is done by considering the average region, average values of this on resistance. Let us say my on resistance is now replaced by an equivalent resistance R equivalent. So how this R equivalent, that is on resistance, equivalent on resistance is calculated. This is calculated by considering the resistance, the average resistance values in the region of operations of interest. So let's say my region of operation interest are T1 and T2. Okay, so the on resistance can be given by this relation, that is 1 by, that is average value between T1 and T2, that is 1 by T2 minus T1 integration T1 to T2 R on T dt. Then R on can be replaced by VDS by ID. Okay, so once you integrate this, you will obtain the value of R equivalent. And the other approach is to simply take the value of R on in region T1 and R on in region T2 and take the average, that is add them and divide by 2. Two approaches are there, right? Now let us apply this approach to find out the R equivalent, that is equivalent on resistance of a MOSFET. Okay, so
time ho gaya, sir.
Okay, time is up. You have any other class after this?
Sir,
We have lunch after that.
Lunch.
Yeah, it's 12:35. So can we wait for 10 minutes? Maybe I'll finish this.
Okay.
Okay, sir.
Okay.
Okay. So we'll utilize the same approach, that is how to calculate the on resistance of the MOSFET. So we'll utilize the same approach. So for calculating the on resistance of this MOSFET, we'll have to first fix the regions of operation of this MOSFET. That is, we need to fix this T1 and T2. Okay, that is this T1 and T2. Okay? That is the regions of operation. So in a MOSFET, in fact, in a CMOS inverter, we had seen while calculating the TPHL. That is, when we were calculating the propagation delay from high to low. So we were interested in calculating the delay between 50% times of the input and output. Okay. So let's say this is my input here. So we mark these 50% points on the input and output waveforms, and between these 50% times of the input and output, we calculated our TPHL. Okay, that is when the output is going from high to low. Okay, so that means my regions of operations could be VDD. Okay, my output is going from high to low. So 50% time point, that is, this is VDD by 2. So two regions of operations one can select, that is VDD to the VDD by 2, because we were trying to calculate TPHL, and TPHL was calculated by considering 50% time between input and output, right? So this time was used to calculate TPHL. So the region of operation could be from VDD to VDD by 2 when we are going from high to low, that is when we are trying to discharge the output capacitance. So the same process is shown over here, that is in this picture. We are trying to discharge this capacitor via this NMOS to ground. Okay, so let's say that initially this capacitor is charged to full VDD. Okay, and we apply a VDD over here at the gate of this MOSFET to switch on this MOSFET. Okay, so as soon as this MOSFET is switched on, the capacitor will start discharging. Okay, that is, this thing will start happening, that is the output will start going from VDD to 0. Okay, this is, let's say, 0 level. But since we are interested in only these two regions, that is VDD and VDD by 2, okay, so we'll say that the two regions of operation. So we'll try to calculate our equivalent resistance in these two regions. Okay, so we modify our previous equation, that is we put here T1 as VDD in this equation and T2 as VDD by 2, right? So when we apply this here, right, so this becomes VDD, T2 minus T1 becomes VDD by 2 minus VDD. So this is minus VDD by 2 should come over here. So that is what is appearing here, minus VDD by 2. Then T1 to T2, that is VDD to VDD by 2. Okay. R on, that is VDS by ID. So we say V by ID in ID saturation. So this MOSFET is in saturation because, in this case, VDS is always greater than VGS minus VT. So when VDD is present here at this point, so obviously this MOSFET is in saturation because VDS is always greater than VGS minus VT. Okay, so the MOSFET is in saturation. So we say that saturation region equation, that is ID sat multiplied by 1 plus lambda V. Okay, so once you solve this, you arrive at this relation: 3 by 4 VDD by ID sat 1 minus 7 by 9 lambda VDD. And ID sat is given by this relation, that is saturation region current equation, that is VDD minus VGS minus VT here. So but VDS is VGS minus VT in saturation. So we arrive at R equivalent, which is given by this relation. Okay. Here. So finally we get R equivalent, which is equal to this one. That is, on resistance is linearized now. So I think I'll stop here and maybe we can discuss in the later class. We'll start from the same point in the later class, next class. So if you have any queries, then maybe you can ask. Otherwise, the class is ended.
Excuse me, sir.
Yeah, please.
Sir, this on resistance will be present only in deep red region, no, sir? Or on
In which region?
Deep triode region.
Always it is present. Yeah, on resistance when the MOSFET is on. Otherwise, the resistance between drain and source is infinite.
Oh, okay, sir. Means it will present. Oh, it will present every time, sir. In saturation, triode also it will be present.
Always it is present. Even when the MOSFET is off between drain and source, you have an infinite resistance.
Okay, sir. Means R1
So when I
equal
say
to
on, yeah, so when I say on, so that means MOSFET should be on, right?
yes, sir. Means R1 equal to 1 by mu n C of W by L into VGS minus VTH.
Yeah, correct. R on is VDS by ID sat. So put the value of ID sat, that is mu n Cox by Cox W by L VGS minus VT into VDS minus VDS square by 2, and put VDS as VGS minus V2 in that equation. So R on is
Okay, sir.
VDS by ID sat.
Okay, sir.
Yeah. Yeah, anything else?
Sir,
Yeah, please.
sir, sir, in the previous slide, you are integrating the R1 with respect to time, sir. Now you are integrating it with respect to voltage. Why
No,
is it
it
so?
is not time. So T1 and T2 are not times, they are regions of operations. They are not times.
Okay, sir.
Yeah, anything else?
Thank you, sir.
Okay, so let us end the meeting. Okay.
Thank you, sir.